Hello, my name is Jeff Messier. I'm a professor in electrical and computer engineering in the Schulich School of Engineering, and this is the seventh lecture in my computer architecture lecture series where I talk about how we represent numbers using binary. Now, to start off the discussion, we'll just get a little bit of terminology out of the way. And most of this terminology will be familiar to you, I'm sure. First of all, we're going to be in this module talking about signed numbers. And signed numbers are basically a system of numbers that allows for positive numbers, negative numbers, and zero. So we can have, plus 3, minus 4.5, and of course, 0. Unsigned numbers allow for positive numbers and zero only. We're not allowed to have negative numbers working with an unsigned number system. The reason why we make the distinction is because when representing numbers using binary digits, sometimes we do use an unsigned number system if we're not worried about, or if it's not important for us to have negative numbers. Integers are whole numbers that can be either signed or unsigned. And real numbers are signed numbers that can represent any point along the line between plus or minus infinity. And we usually represent real numbers using decimals, right? So, the number 2 would be an integer, 2.4 would be a real number, negative 0.8 would be a real number, and so on. And in this module, we're going to be talking about something called floating point numbers and fixed point numbers. And these are binary number representations that are able to store approximations of real numbers. And the reason why I use the word approximation here is, as we're going to see, the accuracy or the precision to which we're able to store numbers using fixed and floating point is limited. And so to kick things off, let's talk about unsigned binary addition first. And this may be something that you have seen in previous courses, so it's possible that this is review. So let's do a simple example where we want to take the number 1 and add it to the number 3. And of course, the number that we're going to get is 4. Now let's represent these numbers as 4-bit unsigned binary numbers. So the number 1 is 0001. The number 3 is 0011. And we want to add these together. So the way that binary addition works is kind of the same way that long addition works with 10-base numbers. You add your two numbers together. So we'll start out by adding 1 and 1. And when you add 1 plus 1 together, your result is 1, 0, or 2. And so this bit gets stored, and the bit to the left is what we refer to as the carry bit. So 1 plus 1 is 2, so we have 0, and we carry the 1. Then we have 1 plus 0 plus 1, which is 2. So we have, again, 0. We carry the 1. Then we have 1 plus 0 plus 0, which is 1. And then finally, we have 0 plus 0, which is 0. And of course, this is the binary representation for 4. So it works. Okay, so now let's talk a little bit about signed binary numbers. And so when dealing with regular old base 10 numbers, when we want to be clear about sign, we will either put a plus or a minus in front of the number. So if we have positive 5, then we would write that as plus 5. If we have negative 3, we would write that as a negative 3. Now, if we're if we were thinking for the very first time about storing signed numbers in binary form, we might very logically say, okay, well, the sign can only take on 2 values, plus or minus. And so why don't we just have a bit on the end of the number that represents sign? So we could add a sign bit. And let's say 0 is equal to positive, and 1 is equal to negative. And so plus 5 could be written as a magnitude of 101. And then our sign bit could be 0. And negative 3 could be written as a magnitude of 0, 1, 1. And we could add a sign bit of 1. But there's a couple of problems with this notation. So what are these problems? Well, the first one is complex hardware. While this number system seems kind of intuitive to us, it turns out that the digital hardware that we would have to implement to perform math with this kind of number system would be pretty complicated. And there's another scheme that we can use that's a lot simpler. The second problem is 2 zeros. 2 values for 0. So we actually, with this number system, have a positive 0 and a negative 0. So we could have 1, 0, 0, 0 as negative 0 and 0, 0, 0, 0 as positive 0. And so this is, while it's kind of a good segue, I guess, into talking about signed binary numbers, this is not how signed binary numbers are actually implemented in most architectures. So the binary signed number system that we're going to be using in this class, and that is used, again, in basically every other architecture, is something called 2's complement signed numbers. And with the 2's complement signed numbers, in concept at least, it's similar to the simple example we did on the previous slide. So the most significant bit is the sign bit, and the most significant bit is equal to 0 for a positive number and 1 for a negative number. So that's the same as on the previous slide. The rest of the bits store the magnitude of the number. So that's also kind of the same, because we had, in our 4-bit example in the previous slide, we had 1 sign bit and then 3 bits for magnitude. What's a little bit different is there is only one 0 representation, and that's when all of the bits are equal to 0. So if we have a 4-bit 2's complement number, then 0 is 0, 0, 0, 0. So there's no such thing as like a positive 0 and a negative 0. Now, when dealing with 2's complement numbers, the 2's complement numbers are basically the same as unsigned binary numbers, except you have an extra 0 on the left-hand side for the sign. So if we wanted to represent the number 6, we would have the magnitude bits. We would have 3 magnitude bits, which would be equal to 110, which is 1 times 4 plus 1 times 2 plus 0 times 1. And then this leftmost bit is the sign bit. And so I included it here, but I really shouldn't have. That's a typo. And so if we have a 0 sign bit, then we just treat the rest of the numbers as magnitude, just like unsigned numbers. This is another typo. So if this is how positive numbers work, how do the negative numbers work? Well, negative numbers are a little bit different. And so just to kind of illustrate that, I'm going to write out the values for a 4-bit 2's complement signed number system. And I'm going to show you first the positive numbers, then I'm going to show you the negative numbers. And you'll be able to see a pattern. You'll be able to see kind of what we're doing. And then in the next slide, I'm going to give you sort of a standard method that you use to create the binary representation of negative 2's complement numbers. And so the maximum value, the maximum positive value that we can represent with a 4-bit 2's complement number is plus 7. And when we have a 4-bit 2's complement number, the first bit is always the sign bit. And because this is positive, the first bit is 0. And then we've got 3 bits to store magnitude. And the biggest magnitude we can store with 3 bits is all ones, 1, 1, 1. And so that's why the maximum positive value is +7. +6 is 0, 1, 1, 0, just like a regular unsigned number. Then we can go down to +5, 4, 3, 2, and 1. And it progresses as you would expect. 0, 1, 0, 1, 0, 1, 0, 0, 0, 0, 1, 1, 0, 0, 1, 0, 0, 0, 0, 1. And as promised, we have only one value for 0, and that's equal to 0, 0, 0, 0. And so far so good. I think that this is pretty intuitive. But what happens now when we wrap around and we want to represent our first negative number, -1? -1 is actually all ones. -2 is 1, 1, 1, 0. -3 is 1, 1, 0, 1. -4, 1, 1, 0, 0. -5, 1, 0, 1, 1. Wrapping it around up here. -6 is 1, 0, 1, 0. -7, 1, 0, 0, 1. And -8 is 1, 0, 0, 0. So first of all, if we look at the leftmost bit is still the sign bit. And when we have a negative number, the sign bit is equal to 1. So that's fine. But then we can look at the magnitudes and we can say, well, these magnitudes don't seem to make sense. They're certainly not like an unsigned binary number. However, if you'll notice, it does seem like we've got a binary counting pattern going on here. We have all ones, and then we have a 0, and then, if you look at the zeros, you can see that this looks like a binary counting pattern, except our bits are inverted, where the zeros behave like ones and the ones behave like zeros. And this is basically how 2's complement works. So the leftmost bit is the sign bit. It's equal to 1 if there's a negative number. And then the magnitude is basically the bitwise inversion of what a normal magnitude should be, offset by 1. And that offset is necessary to get rid of the problem of the 2 representations for 0. And so here's the procedure for finding the binary representation of a negative number when you're using 2's complement. Step 1 is to find the binary representation of the positive number. Oops, maybe I'll use red. Step 1. And so that's just, if you want to, let's say, represent -12, step 1 is to find just the unsigned regular old binary number for +12. Then perform the bitwise inversion of that number. Just turn all the ones to zeros and zeros to ones. And then the last step, and this is to add that offset that we talked about on the previous slide, the last step is to add 1. And so let's do a quick example of what this looks like. So let's say we want to find the 2's complement number, or find the 2's complement binary representation for -3. And so step 1, Find the binary number for positive 3. Right? So take your magnitude, or another way is like find the binary representation for your magnitude, right? So negative is the sign, but 3 is the magnitude. And so if we're dealing with, let's say again, a 4-bit 2's complement number, like we were on the previous slide, the representation for positive 3 would be 0, because we're dealing with a positive number. And then our magnitude is 0, 1, 1, right? So again, positive numbers in 2's complement are just like regular old unsigned binary numbers. Step 2, bitwise inversion. So 0, 0, 1, 1 is transformed to 1, 1, 0, 0. And then step 3 is add 1. And so we take our bitwise inverted number 1, 1, 0, 0, and we just add 1. And this, again, is just binary addition. So 0 plus 1 is 1. And then you basically assume that we've just got zeros in these gaps. So 0 plus 0 is 0, 1 plus 0 is 1, and 1. And so this is our answer. And if you go back to the previous slide where we kind of counted them all down, sure enough, that's the number. And so that's the kind of the procedure to create the negative numbers. And at this point, you might say, yeah, I can kind of understand how this works, but it doesn't seem to be super easy, or doesn't seem to be super intuitive, for example. And it's true, like we do have this kind of unusual representation, and until you're used to it, it's sort of hard to just kind of easily look at 2's complement negative numbers and then immediately convert it to a base 10 number in your head, like you can maybe for positive numbers if you're more used to it. However, from a conceptual human perspective, we did get rid of the problem of having 2 zeros, right? So we only have 1 0. And in the next module, when we, a little bit in this module, but certainly in the next module, you'll see how using 2's complement really simplifies the design of the digital hardware of the ALU. And just to kind of, I guess, close things off, just talking about the range of 2's complement numbers. This is sort of the general expression for the biggest positive number and the biggest negative number you can store with 2's complement. So the largest positive value, if we're dealing with, if n is the number of bits, then the largest positive value is 2 to the n minus 1 minus 1. And the smallest, or the most negative value, is minus 2 to the n minus 1. And so very specifically, let's say n is equal to 4 bits, like it was in our previous example. So I guess the most positive number we can represent would be 2 to the 4 minus 3 minus 1, which is 2 to the, not to the 4 minus 3, to the 4 minus 1, which is 2 to the 3 minus 1. So that's positive 7. And we saw that in our previous example. And then the most negative number we can represent is 2 to the 4 minus 1, negative 2 to the 4 minus 1, which is negative 2 to the 3, which is equal to minus 8. And so we can go from positive 7 to minus 8. And always with 2's complement numbers, we have one negative number, negative 8, that doesn't have a positive counterpart. And we call that number the weird number. So the weird number for 4-bit 2's complement is negative 8. Okay, so in this module, we're going to look at 2 number systems for representing real numbers, or numbers with a fractional component. And those 2 systems are the fixed point system and the floating point system. And we're going to look at the fixed point system first, just because it's a little easier to understand. And it's also a little bit more limited. Now, As you're going to see by the end of this module, the fixed point system is definitely simpler than the floating point system. And it allows us, as we're going to see in the next lecture, it basically allows us to continue to use basic sort of integer mathematical operations to operate on real numbers as well. And as a result, fixed point numbers tend to be used in applications where speed is really important. So you see fixed point being used a lot in digital signal processing, sort of specialty digital signal processing applications. And so basically, fixed point numbers are one alternative for approximating real numbers using a binary digit. Again, we don't have infinite precision here. We've got a finite amount of precision, and you'll see what I mean by that. For an r-bit fixed point number, we place a binary point between two of the bits. This is very, very analogous to the decimal point. So when I write the number 3.14, of course, we know that that little dot is what we refer to as the decimal point. When we're writing out fixed point numbers, I will write a number like 101.01011. Right? And so this is basically what a fixed, conceptually how a fixed point number is written out. This point, however, we don't refer to as a decimal point because the prefix deci comes from 10. And so decimal is only appropriate when we're working with 10-base numbers. Instead, we call this a binary point rather than a decimal point because we're working in base 2 numbers. Now, similar to 10-base numbers, we have to make a decision about what kind of precision we want to use when representing our real number. So for example, I could write a number as 1.5, or I could write a number as 1.483217. Obviously, the second number is representing the real number with greater precision because we're using more digits to the right of the decimal point. And we have basically exactly the same thing with fixed point numbers. So I could write a number as 101.0, or I could write a number as 101.01011. And this second one, just like for base 10 numbers, the second one represents a real number with a greater degree of precision because we're allocating more bits to the fractional part of the number. However, of course, the cost of that is to use more storage, right? The more precision we want to use, the more storage or the more bits our number takes up. And so to help us kind of specify how many bits we're choosing to use to represent the integer and fractional portions of the number, we can use something called Q format notation. And so in general, we have a capital Q followed by a number, a dot, and then a number. And this refers to an n plus m plus 1 bit fixed point number with 1 sign bit, m integer bits, and n fractional bits. And so let me do an example here. So let's consider the case where we've got a Q 2.5 number. So the number 2 indicates how many bits we're using to represent the integer portion of the number. And the number 5 represents the number of bits that we use to represent the fractional portion of the number. And always with fixed point numbers, there's an additional bit that we use for the sign bit. And so a Q 2.5 number is actually an 8-bit number. And so we start off with a sign bit. We then have 2 integer bits. I'll represent those as 2 W's. And then we have 5 fractional bits. And so this is how our number would be laid out. We have the most significant bit is a sign bit. We then have the 2 bits allocated for to store our integer. And then we have the 5 bits allocated to store our fraction. Okay, the next question is how to convert fixed point numbers into base 10 numbers and base 10 numbers back into fixed point numbers. And so let's go from fixed point to base 10 first. Basically, the way we figure out the base 10 representation for a fixed point is to multiply each bit by a power of 2, where the exponent has to do with the position of the bit, just like normal, right? So for regular old unsigned numbers, for example, 0, 1, 1 is equal to 0 times 2 to the power of 2 plus 1 times 2 to the power of 1 plus 1 times 2 to the power of 0. Fixed point numbers are basically exactly the same, except that the bits to the right of the binary point have negative exponents. And this is most easily illustrated with an example. It's pretty straightforward. So in this example, we have a Q 2.5 fixed point number, 0, 1, 0, 1, 0, 1, 1, 0, and we want to convert it into base 10. So again, just a review of what this Q notation means. It means the first bit is going to be the sign bit. So the 0 is the sign bit. The next two bits, 1, 0, are the integers, and then the remaining 5 bits, 1, 0, 1, 1, 0, are the fractional. And so this is the sign bit, this is the integer portion, and then this is the fractional portion of the number. And just like in 2's complement, a sign bit of 0 means a positive number, a sign bit of 1 means a negative number. And we'll get to negative fixed point numbers in a second. And so we know that the number is positive, so we can basically kind of discount that first bit. And I'm going to put in the binary point just for reference. And so the base 10 value of this fixed point number is 1 times 2 to the 1, that's this bit, plus 0 times 2 to the 0, that's this bit. So far so good. This is just like regular old integer binary numbers. This bit is 1 times 2 to the minus 1. This bit is 0 times 2 to the minus 2. This bit is 1 times 2 to the minus 3 plus 1 times 2 to the minus 4 plus 0 times 2 to the minus 5. And so you can hopefully see how this fractional stuff works, right? So the first bit after the binary point is multiplied by 2 to the minus 1. The second bit is 2 to the minus 2, 2 to the minus 3, and so on. If I then sort of write out what these numbers are actually equal to, we have 2, and I'm not going to write the 0, well, no, I will write the 0 terms, plus 0, plus 1 times 2 to the minus 1 is 0.5. Then we have another 0 term, and then 0.125, and then 0.0625 plus 0 is equal to 2.6875. And that's how it works. So you can see now, hopefully, that fixed point numbers, the integer part is just like regular old integer binary numbers that we've been working with up until now. And the fractional part, also very similar, except it's just inverse powers of 2. So the first bit can represent the first bit to the right of the binary point represents a half. The second bit to the right of the binary point represents a quarter. The third bit to the right of the binary point represents an eighth, and so on. Okay, so as I mentioned earlier, the location of the binary point, or basically how many bits we allocate to the fraction, determines the precision of our number. And very specifically, the resolution, or in other words, the minimum step size of our fixed point number, of a QMN fixed point number is 2, this should be 2 to the minus n. So for example, in our 5-bit, in our previous example where we had 5 bits, our minimum step, in our previous example where we had 5 bits allocated to the fractional portion of the number, our minimum step size would be 2 to the minus 5. And so based on the accuracy you require for your application, you can kind of decide where to put your binary point. Now, another concept that's useful when working with fixed point numbers is the notion of a scaling factor. And this is going to be handy when we convert base 10 numbers into fixed point representation. And so when writing out base 10 real numbers, we can think of numbers with a fractional point or a fractional component as being multiplied by a scaling factor. So let me show you what I mean. So let's say we've got a number 123.45. We can think of this as the integer 1, 2, 3, 4, 5 multiplied by a scaling factor 1 over 100, right? And so, or we can think of it as an integer multiplied by 1 over 10 squared. If we had 123.456, we can think of this as the integer 123.456 multiplied by a scaling factor 1 over 10 cubed. And so basically any base 10 real number that we choose to write out, we can represent as a whole number, an integer, multiplied by a scaling factor, 1 over 10 to an exponent, and the exponent is basically the number of digits that we choose for our fractional part. So this concept of the scaling factor can be extended to fixed point numbers as well. So in our previous example, we saw that the number 2.687 was equivalent to the Q2.5 number 10.10110. And I'm not representing the sign bit here. So this is equal to the integer 1010110 multiplied by a scaling factor 1 over 2 to the 5. Exactly like the scaling factor for the 10 base numbers, where we multiplied by 1 over 10, and the exponent of 10 was the number of digits we allocated to the fractional part. Now we're multiplying by 1 over 2, and the exponent is the number of digits that we represent using that we choose to represent the fractional part. And so if we look at the integer value of this regular number, this is 87. And if we multiply 87 by 1 over 2 to the 5th, if you check this with your calculator, we get 2.687. And so we can basically take the integer form of our fixed point number and determine that integer value just as we always have done, and then multiply it by 1 over 2. This looks like a 25. I'll make that a little bit more clear. 1 over 2 to the 5th to get the real number value. And so this is maybe a second way to convert from or to convert a a fixed point number into base 10. But as it turns out, this scaling factor trick is going to be useful for us when we want to convert a real number into fixed point binary representation. So now let's look at how to convert a base 10 real number into fixed point representation. So when we want to determine the q m.n representation of a real number, the first thing we do is we multiply it by the inverse of that number's scaling factor. So if we have n bits assigned to represent the fractional part of the fixed point number, then we multiply our real number by 2 to the n. Then our fixed point number is just the integer portion of the result of that multiplication. And so it's kind of hard to say in general, but it's way easier to illustrate with an example. So let me show you. So what we want to do is we want to figure out the q 2.5 fixed point representation of this real number. And so the first thing we do is we take our desired real number and we multiply it by the inverse of the scaling factor. So we take 1.78125 and we multiply it by 2 to the 5, which is the inverse of the scaling factor. And again, 5 is the number of bits we've allocated for the fraction in our fixed point number. The result of this multiplication is 57. And if I represent 57 as a binary number, it looks like this: 0, 0, 1, 1, 1, 0, 0, 1. And that's it. That's our fixed point number. Or if you want me to sort of be a little bit more explicit, this is the sign bit. These are the two integer bits. And so, excuse me, these are the two integer bits. So the binary point goes there. And if we convert this back into 10 base, we would have, and I'll leave out the 0 terms here. So we would have 1 times 2 to the 0 plus 1 times 2 to the minus 1 plus 1 times 2 to the minus 2 plus 1 times 2 to the minus 5, which sure enough equals 1.78125. I kind of ran out of room there. So that's it. You take your real number, you multiply it by the scaling factor, and then you take the integer that you get and you just represent that as binary. And when you put the binary point in the right location, that is your fixed point number, basically. But of course, we're not always going to be able to represent our number, our real number with, exact precision, because the precision of fixed point numbers are limited. So let's take a second example where we want to represent 3.141593 as a q 2.5 fixed point number. So again, we take our desired real number, 1593. We multiply it by 2 to the raised to the power of 5. And in this case, we don't get a whole number. We get 100.530975. And so what we do is we, when converting into our fixed point number, we just take we get rid of the fractional part and we represent only the integer portion of our number as in binary. So if we take the number 100 and we represent it as binary, that's 11001000. And so our fixed point number, again, would be, and we're not showing the sign bit here, 11.00100. However, if we then took this fixed point number and converted it back into base 10, we would get, and again, I'm not going to show the 0 terms, we would get 1 times 2 to the, 1 times 2 to the 1 plus 1 times 2 to the 0 plus 1 times 2 to the minus 3. Whoops, 3, that's not very good, 3. Which is equal to 3.125. And so if you compare this number with our original desired number, you can see the error that we introduce by representing our desired real number by this relatively crude and limited fixed point representation. If you wanted better accuracy, you would use a bigger number, right? You would, rather than limiting yourself to an 8-bit number, you would maybe take a 16-bit or a 32-bit number and have way more bits available for the fractional and the integer part. Okay, so fixed point numbers can also be used to represent negative numbers. And negative fixed point numbers are just the 2's complement of their positive counterparts. So it's relatively straightforward. So to start out with an example, let's determine the Q 2.5 fixed point representation for negative 1.9781. And so the way this works is we just figure out the fixed point representation of the positive version of our real number, and then we just take the 2's complement inversion. So I'm going to take minus 1.9781, multiply it by the inverse of our scaling factor, 2 to the 5th, which gives us minus 63.2992. Oops. And we discard the fractional part again, so we're going to work with just negative 63. And the positive binary representation of 63 is 0, 1, 1, 5. So 0 followed by 7 ones, if I've counted that out properly. No, sorry, 0 followed by 6 ones. And then we just take the 2's complement inversion of that and add the sign bit. So this is our sign bit now. And the rest of the number is 1. There, I think I've got that right. Yes, exactly. And that's it. Now to go the other direction, basically, if you want to take a negative fixed point number and determine the base 10 value, you do the 2's complement inversion of it first, and then just treat it basically like a positive fixed point number with a negative sign in front of it. And so if we reverse our previous example to determine the base 10 value of the Q 2.5 number 1, 1, 5 zeros, and then 1, the way 1, 1, 2, 3, 4, 5, 1. We then just treat this as the negative of 0, 1, 2, 3, 4, 5, 6. Or, again, to put in the binary point, 1, 2, 3, 4, 5, which is the negative of, whoops, the negative of 1 times 2 to the 0 plus 1 times 2 to the minus 1 plus 1 times 2 to the minus 2 plus 1 times 2 to the minus 3 minus 4 which is equal to, if you calculate it all out, 1.96875, which is the value that we started with on the previous slide. So that concludes our discussion of fixed point numbers, and now I want to move on to talk about floating point numbers. And first of all, just a little bit of an explanation about where the names come from. So fixed point numbers are named because the binary point is always in the same location. The binary point is fixed. So if we are working with, let's say, Q 3.2 numbers, we will have one sign bit, 3 integer bits, the binary point, and then 2 fractional bits. And the binary point is always there. So there's always 2 integer bits to the left and always, 3 integer bits to the left and 2 fractional bits to the right. Floating point is named because we can imagine its binary point as floating around a little bit. And this is hopefully a familiar concept because this is what happens with regular base 10 scientific notation. And so this slide is just a bit of a review. Now, big picture, as we know, engineers and scientists can work with numbers that are extremely large. So the number of bytes of information stored on the internet, for example, is extremely large. And also numbers that are extremely small. So the width of a transistor, how many meters of wide is a transistor, is a very, very small number. It's an extremely small fraction of a meter. And so sometimes the number that we want to work with is right around 0. So 3.14 is a number that's pretty close to 0. Sometimes, however, we have a very, very small number that we want to work with, and other times we have a very, very big number. Now, with these second two numbers, it's a real hassle to have to put, a decimal point, a huge number of zeros before we get to our number. And with this third number, it's also kind of a hassle to have to write down every single group of numbers that make up the overall digit. And so scientific notation is something that we use to help us with this problem, basically. Now, sometimes scientific notation is not really that necessary. So, and that's the case for our first example. So 3.14 represented as scientific notation is 3.14 times 10 to the 0. So in fact, we made the number a little bit more difficult to write out. However, for the second number, this, 0 point, a whole bunch of zeros, 1, 2, 4, 6, becomes a lot more straightforward to write out. We write it as negative 1.246 times 10 to the minus 13. And the minus 13 indicates that we had to move the decimal point 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 places to put it between the 1 and the 2. The third number we can represent as 1.344 times 10 to the 16. And this refers to the fact that we had to jump the decimal point 16 places. I'm not showing this exactly, obviously. 16 places to put it between the 1 and the 3. And this is familiar. You've been working with scientific notation for a while. One of the consequences of scientific notation sometimes is that we don't represent the entire number, or we sacrifice precision. So, and this is the case with our third example. So we have 13, 4, 3, 5, 1, 2, 3, 9, 7, 8, 100, 3, 4, 5. Like that's a huge number. And then when we represent it with scientific notation, we're basically only representing the first 4 digits rounded up. So we've lost some information. We've lost some precision. And as we're going to see, floating point numbers are the binary counterpart of 10-base scientific notation. And just like 10-base scientific notation, sometimes with floating point numbers, we're going to have to sacrifice some precision as well. Now, just a little bit of a bit of terminology that, again, is probably a bit of a review. When we look at our scientific notation number, we can divide it into 2 parts. This first part, the negative 1.24691, we can refer to as the significand or the mantissa. I'm going to be calling it the mantissa in this lecture. And this term, or more specifically the exponent, is the order of magnitude or the exponent, negative 13. And so I'm going to be referring to the exponent when I talk about floating point numbers. So just like scientific notation, floating point numbers have a sign, a mantissa, and an exponent. It's just that everything is in binary. And so if we were to, let's say, create or represent an 8-bit floating point number, the leftmost bit in a floating point number is always the sign bit. So the first bit would be equal, the first bit is equal to the sign. The next bits are the exponent bits. And so let's say the next 3 bits in this example are equal to the exponent. And then the remaining 4 bits represent the mantissa of the number. And the number of bits that we allocate to the exponent and mantissa and the overall length of the floating point number will change the precision and the range of the numbers that we can represent. And we'll talk about that a little bit more as we get into this. If we were to calculate the base 10 value of the number represented by this binary floating point, it would be equal to -1 raised to the exponent of s. So if s is 0, we have a positive number. If s is 1, we have a negative number. We then multiply that sign by the value of our mantissa. And our mantissa is equal to 1 dot xxxx base 2. This is equal to a fixed point number. So the mantissa is basically always a fixed point number, with the most significant bit being equal to 1. And again, I'll talk a little bit more about how that works. The mantissa and the sign is then multiplied by 2 raised to the exponent of the value of the number contained in our exponent bits minus something I'm going to call a bias term. And I'm going to explain that as well. So I'm going to explain all of this in more detail. It's kind of hard to understand exactly how this works at this point. But I just wanted to introduce this as the general format and to try and link floating point in your minds to our discussion of scientific notation. So floating point numbers basically have the same format as scientific notation. We've got a sign, we've got a mantissa represented in fixed point binary format, and we have an exponent, but rather than multiply by 10, we multiply by 2 raised to the exponent because we're working in binary. And so just to put a little bit more detail around this, floating point numbers consist of a single sign bit. The mantissa and exponent are represented in the same way for positive and negative values. So basically, we do not use 2's complement for floating point numbers. The mantissa is always represented as a positive number, and the value of the sign bit just indicates whether it's positive or negative. The mantissa is equal to a positive fixed point number, a q1.n number, where n is the number of mantissa bits in the floating point number. So if we go back to our example here, this would be equivalent to a q1.4 fixed point number. That's how we represent the mantissa. The exponent value, the value stored in these y bits, is adjusted so that the most significant 1 bit in the floating point or in the fixed point mantissa is always to the left of the binary point. Now, this seems like a strange statement, but let's go back to our discussion of scientific notation. Remember, for scientific notation, we always hop our decimal so that we have a non-zero number, a single non-zero digit to the left of our decimal point. Same thing here. We hop it all the way along. And so we have 1.34 times 10 to the something and 1.246 times 10 to the something. We do exactly the same thing with floating point numbers. We have a fixed point mantissa, and we hop the decimal point all way along, so until we have a 1 just to the left of our decimal point, or sorry, our binary point. And the number of hops that we take to move our binary point along basically determines the value of our exponent, just like it does for scientific notation. Just one other small note, since there's always a 1 to the left of the binary point, it's not stored, right? So it's understood that we always have a 1 to the left of our binary point, so we don't store it. We end up just using all of our mantissa bits to store the fractional value on the right-hand side of the binary point, sorry, not the decimal point. Now the exponent value, both positive and negative exponents are required. So if we hop our binary point to the left, we need a positive exponent, just like we do when we hop the decimal point for scientific notation to the left. When we hop the binary point to the right, we need a negative exponent. And that means we need to be able to represent positive and negative exponent values. We do not use 2's complement here either. Instead, we have a bias term that is subtracted from the positive binary values stored in the exponent. So we have a positive number stored in our 3 exponent bits, and then we subtract a bias term. And for an r-bit exponent, in this case, if r was equal to 3, the bias term is equal to 2 to the r minus 1. So for example, if we have 8 exponent bits, the bias is equal to 2 to the 8 minus 1, or 127. If we have 3 exponent bits, we have 2 to the 3 minus 1, or 3. Now, it's hard to, at this point, kind of understand, like, what's this bias term and what's this sort of fixed point mantissa and stuff. But these are all the general ideas around floating point. And what we're going to do next is we're going to move into some examples, and I'm going to sort of work with some specific numbers, and hopefully you can see how this all fits together. Okay, so let's tie everything together by working through a few examples. And the best way to do that is to look at first how to convert binary floating point numbers into base 10 numbers, and then look at how to convert a base 10 number into a binary floating point number. And as you would imagine, there's a series of steps for each of these operations. So starting with floating point to base 10 conversion, the first step is to determine the sign of the number according to the expression -1 to the exponent of s, where s is the sign bit. So if s is equal to 0, this term is equal to 1, and if s is equal to 1, it's equal to -1. So 0 is a positive number, 1 is a negative number. The next step is to calculate the value of your mantissa. So if you have k mantissa bits, you calculate the value just like you would a q1.k fixed point number, where the integer bit is always equal to 1. So this draws on what we've learned about fixed point numbers. The final step is to calculate the 2 to the exponent value term, and the exponent value is equal to the positive binary number represented by the exponent bits minus a bias term, and as I mentioned, the bias term is equal to 2 to the r minus 1 for an r-bit exponent. And then you basically just multiply your sign term, the base 10 value of your fixed point mantissa, and your 2 to the exponent value term all together to get your base 10 value. So let's now put those steps into action and work through an actual example. Okay, so let's do an example. Okay, so let's do an example to sort of tie all of this together. So In this example, we're going to figure out the base 10 value of a floating point number. We're going to use the same 8-bit floating point number that we introduced at the start of our discussion of floating point. So we're going to use k is equal to 4 mantissa bits, and r is equal to 3 exponent bits. And so step 1 is to figure out the sign of our base 10 number. The sign bit is always the most significant bit in your floating point binary number. In this case, the sign is equal to 1. The base 10 value of the base 10 sign value of our number is equal to -1 to the sign bit. In this case, we have -1 to the 1. Or in other words, -1. So we're dealing with a negative base 10 value. The next thing we need to do is figure out the value of our mantissa. Now we have 4 mantissa bits. Our mantissa bits are always the least significant bits on our floating point number. And our mantissa is always equal to q to the, or in this case is equal to q to the 1.4 fixed point number, where 4 is our mantissa bits, or the number of mantissa bits. And so this is equal to 1.0101 in binary. These fractional bits are what's stored in the actual floating point number, and this single integer bit equal to 1, again, that's understood, so we don't store it. So just converting this to a base 10 value using standard fixed point techniques, this is equal to 1, the value of our fractional bit, plus 2 to the -2, plus 2 to the -4, which is equal to 1.3125. So now the final step is to determine the value of our exponent. The first thing we need to do is figure out the value of our bias term. Because we have 3 exponent bits, the value of our bias term, again, is r -1 to the -1, which is equal to 2 to the 3 -1 -1, or 3. Now our exponent value is equal to the value of the number stored in our exponent bits minus our bias. Now our exponent bits are equal to 0, 1, 0, or in other words, it's which is equal to 2. Our bias term is equal to 3, and so our exponent value is equal to -1. So the final base 10 value of our floating point number is equal to our negative sign multiplied by the value of our mantissa, 1.3125, multiplied by 2 to the exponent value, which is equal to -1. And this ends up being equal to negative 0.65625. And so this is the base 10 number represented by our floating point, our binary floating point number given by 10100101. Okay, so there are actually quite a few, so converting a base 10 number into floating point involves quite a few steps. So in the next few slides, I've listed all the steps, so I'm just going to kind of quickly go through them at sort of a high level, and then I'm going to do an example. And it's really sort of in the going through the example that you really hopefully see how all of these steps work. So step 1, when converting a base 10 number into a floating point number, so let's say we wanted to convert minus 2.7014 into a floating point number. Step 1 is to determine the sign bit value. Step 1 is easy. So if it's a negative number, s is equal to 1, otherwise s is equal to 0. Once you've determined the sign bit, you can get rid of the sign and just treat the number as a positive number going forward. The first sort of group of steps that we're going to go through involve determining the mantissa. Now, our number potentially, in this case it does, our number potentially has an integer component and a fractional component. So the integer component is 2 and the fractional component is 0.7014. The first step in determining our mantissa is just to represent the integer component of our number in binary. And so we would represent the number 2 in binary. And after our integer component, we put our binary point, just like we had a binary point in our fixed point numbers. The next step, if we have a fractional component, is to determine the mantissa representation of the fractional component. And to do that, we do sort of a series of steps. So we multiply the fractional component by 2, and if that's enough to create an integer component in our number, then our mantissa bit is equal to 1. And if it's not, then our mantissa bit is equal to 0. Then we multiply by 2 again, check if we have an integer component. If we do, the mantissa bit is 1. And if we don't, the mantissa bit is 0. Every time we do have an integer component, once we set our mantissa bit to 1, we subtract off that integer component. And what's the intuition behind this? Well, basically, we're trying to figure out the binary number that represents our fractional component. And when you multiply something by 2, it's equivalent to shifting that number left 1 position. And so you can imagine we're just taking the binary component or the binary representation of our fractional component, shifting it left. Every time we have an integer component, after we multiply by 2, it's just like having a 1 sort of pop up above our binary point, and then we just record a 1, otherwise we record a 0. Once we've determined our mantissa, we'll have our integer component and our fractional component. We then need to adjust the location of our binary point left or right so that we have only a single 1 to the left of the binary point. And again, this is very analogous to scientific notation because if we have, for example, 214.7 and we want to represent it in scientific notation, we hop the decimal point 2 places to the left, and we have 2.147 times 10 to the 2. And we do the same thing with floating point numbers, except we're moving our binary point around. Once we've got the binary point in the right location, we then determine the value of our exponent bits. Okay, so this is a very high level description of all of the steps. You're probably not clearly seeing how to do this exactly yet. So what I'm going to do on the next slide is I'm going to work through an example where we're going to go through all of these steps in detail. Okay, so let's work through our example. So we are going to, in this example, determine the 8-bit floating point value of minus 2.7014, and we're going to use the same 8-bit floating point number that we've been working with up until now, where we have 3 exponent bits and 4 mantissa bits. So step 1, determine the sign bit. S is equal to 1 since we're dealing with a negative number. Step 2, we just take the absolute value of our number. We strip off the sign bit because we've already recorded it. Step 3. Step 3 is where we represent the integer component of our number as a binary number. So number 2 is represented as 10. So our integer component is equal to 10, and we put the binary point right after our integer component. Now we need to determine the integer representation of the fractional bits. Or sorry, not the fractional bits, the fractional component, 0.7014. And so what I'm going to do is I'm going to take or 0.7014, I'm going to multiply it by 2. That equals 1.4028. Now, after multiplying by 2, we have an integer component, right? So you can imagine multiplying by 2, we're shifting our fractional bits to the left. And because we have a 1, because we have an integer component here, we've had a 1 sort of shift to the left of our decimal point or our binary point. And so this means we're going to set our mantissa bit, our next mantissa bit, to 1. We then subtract off our integer component. And so in our next step, we multiply 0.4028 by 2. Right? So we subtract off our integer component. We're left with 0.4028. We multiply it by 2, and we get 0.8056. This does not have an integer component, and so we set our mantissa bit to 0. We multiply 0.8056 by 2 in our next step. And we get 1.6112. That has an integer component, so we need to subtract it off. And we set our mantissa bit for this current step equal to 1. Now, we could keep going, right? We keep multiplying by 2, subtracting things off or whatever. But if you'll notice, we now have enough bits. And so in our next step, and I think my steps now maybe don't line up with the steps on the previous slide, but we're working through it in sequence anyways. In our next step, we have our mantissa. We now have our integer component, 1, 0, then our binary point, and then we have these bits, 1, 0, 1. And so this is our mantissa represented in binary. But now, just like scientific notation, we need to adjust our binary point so that we only have a single 1 to the left of our binary point. And that means we're going to hop the binary point 1 position to the left. And so this means we're going to result in a final mantissa of 1.0101, and we moved our binary point 1 position to the left. Now, since we moved our binary point 1 position to the left, our exponent value is going to equal +1. Now, we know our bias term for our exponent is equal to 2 to the 3 minus 1 minus 1, in other words, equal to 3. And so the actual value stored in our exponent bits is equal to our exponent value plus our bias. So it's equal to +1 plus 3, or 4. And so our final floating point number then is 1, because we have a negative number. Our 3 exponent bits need to represent the number 4, so we have 1, 0, 0. And then our 4 mantissa bits are the 4 bits to the right of the decimal point, or 0, 1, 0, 1. So just to kind of close the circle on this example, I'm now going to convert our floating point number that we created on the previous slide back into base 10. I always like to do this. It's sort of a useful check. You often won't exactly match because of the limited precision of the floating point number, but it's still useful to do it. And so if we start writing this out as a base 10 number, we have -1 raised to the power of 1, right? Because our sign bit is equal to 1. We now then create our mantissa term. Now our mantissa, remember, is a fixed point number that is equal to 1 dot 0, in this case 0, 1, 0, 1. And so that's equal to 1 plus 2 to the minus 2 plus 2 to the minus 4. Now, our final term is 2 raised to our exponent value. Now, because our exponent bits are equal to 4, the value of our exponent is equal to 4 minus our bias term, which is 3. And if we do this calculation, we get minus 2.625. And so we don't exactly match the number that we started out with, but we get close. And the difference in error is due to the limited precision of our floating point number. Now, in this lecture, I've used 8-bit floating point numbers just because it makes it a little easier to move through the examples. But in reality, real floating point numbers are much, much bigger than 8 bits. The most common floating point number standard is the IEEE 754 standard. So as a designer, it's really kind of up to you how many bits or how long you want to make your floating point number, how many bits you want to assign to your exponent, how many bits you want to assign to your mantissa. But in practice, most computer architectures conform to the 754 standard. And this standard has both single and double precision floating point numbers. A single precision floating point number is 32 bits long. It has 1 sign bit, 8 exponent bits, and 23 mantissa bits. Double precision, 1 sign bit, 11 exponent bits, and 52 mantissa bits. And you may have already used this if you've done any sort of C programming, because when you create a float variable, it's typically a single precision floating point number. And if you create a double floating point variable, it's typically, as the name suggests, a double precision floating point number. The IEEE standard also has some special values. It can represent plus or minus infinity. And to represent infinity, all the mantissa bits are zeros, the exponents bits are all ones, and the sign indicates if it's a positive or negative infinity. And you can also represent not a number. So maybe if you've done some work in Python and you've divided 0 by 0, you've got not a number value. And that's represented in the floating point standard as some mantissa bits can be non-zero, the exponent bits are all ones, and the sign is irrelevant.